Hamming code. Hamming code is a 1-bit error correction method which is commonly used. We have seen in the previous video that for 1-bit error correction, the minimum Hamming distance required is 3. If the distance between two valid code words is at least 3, then if an error occurs or if an invalid code word is generated, then we can find the actual valid code word before error, which will be the valid code word 1-bit distance away from the invalid code word. Also, we saw that we can alter the Hamming distance by adding parity bits or redundant bits. Hamming code is a method which ensures a minimum Hamming distance of 3 by adding multiple parity bits or multiple redundant bits. And finding the actual valid code word which is 1-bit distance away by comparison will be time consuming. So in this method, the redundant bits are added in a particular way which provides an easy way to identify the position of error. So let's see how Hamming code works. If we have some data, we will consider it as blocks of data bits, such that each block will be having a particular number of data bits, and to each block we add multiple parity bits, such that each parity bit will take care of a particular collection of data bits within that block. So first of all, what should be the number of data bits within each block, and what should be the number of redundant bits to be added to each block? A very common code used is Hamming code 74, in which for every 4-bit data, 3 parity bits are added to form a 7-bit valid code word. So how these values 4 and 3 are determined? Suppose for each block of m data bits, we add n number of redundant bits to form a valid code word of m plus n bits. So in our example of code 74, to the 4 data bits we add 3 redundant bits to form a 7-bit valid code word. And we are dealing with 1-bit error correction. So which all are the chances of that 1-bit error? Sometimes bit 1 may be corrupted, or bit 2 may be corrupted, or bit 3 may be corrupted, or there may be error at bit 4 or 5 or 6 or 7, or there may be no error at all. Similarly, for m plus n bits, there may be error at bit 1 or at bit 2 and so on, and at last there may be error at bit m plus n, or there may be no error at all. So total, how many cases we have to consider? In this case, there may be error at one of these 7 bits, or there may be no error at all. Hence total 7 plus 1, 8 cases we have to consider. Thus generally, if there are m plus n bits, one of these m plus n bits may be corrupted, or none of the bits are corrupted. Hence total m plus n plus 1 cases have to consider. And to identify each of these cases, we have n number of parity bits. Using n bits, how many cases we can consider, or maximum how many combinations are possible? 2 to the power n combinations are possible. With all these, we should be able to cover m plus n plus 1 cases. For that, the condition is 2 to the power n should be greater than or equal to m plus n plus 1. So based on this equation and based on other factors to consider, a proper value for m and n should be chosen. In our example, suppose the size of data bits is decided to be 4. Then what should be the value of n which satisfy this condition? 2 to the power n should be greater than or equal to 4 plus n plus 1, means 2 to the power n should be greater than or equal to 5 plus n. If n equals 1, the condition never satisfies. If n equals 2, it never satisfies. If n equals 3, the condition is satisfied. So The minimum value of n, the minimum number of redundant bits should be always added. So what should be the minimum value of n which satisfies this condition? N equals 3. Now instead of 4, suppose m equals 3. The number of data bits is decided to be 3. Then what should be the value of n to satisfy this condition? N equals 1 will never be fine, n equals 2 will never satisfy, and n equals 3 it's fine. 2 to the power 3, 8 is greater than m plus n plus 1, which is 7. So for 4 data bits we have to add 3 redundant bits, and for 3 data bits also we have to add 3 redundant bits. And if m equals 5, if the number of data bits is 5, then what should be the number of redundant bits to be added? 2 to the power 3, 8 is not greater than 9, hence this condition never satisfies. This 2 to the power 4, 16 is greater than 10, hence n equals 4. The minimum value of n which satisfies the condition is 4. So for 5 data bits we have to add 4 redundant bits. So based on all many factors, a proper length of data bits will be decided, and based on that length of data bit, the number of parity bits will be decided. So we have decided the value of m and n, the length of data bits, and the number of redundant bits to be added. Now, where will we place these parity bits? At the beginning, or at the end, or in the middle? According to Hamming code, there is a rule for it. The parity bits are always placed at the positions powers of 2. Suppose in our example, our valid code word is having m plus n equals 7 bits, and the bits are positioned from right to left. Then all powers of 2 positions will occupy the parity bit, and the remaining will be kept for data bits. So why they are kept at positions powers of 2? We have seen that every parity bit will be taking care of a particular collection of data bits in that code word, and which are the data bits to be taken care of by a particular parity bit is determined by the position of that parity bit. Because every number can be represented as the sum of powers of 2, hence every bit position can be represented as the sum of powers of 2. For example, 1 is 2 to the power 0, 2 is 2 to the power 1, and 3 is 2 to the power 1 plus 2 to the power 0, 4 is 2 to the power 2, and so on. Now, the parity bit at the position 2 to the power 0, that is the parity bit at the position 1, will take care of the data bits at all these positions 3, 5, 7, 9, and so on. Similarly, the parity bit at the position 2 to the power 1, that is the parity bit at the position 2, will take care of all these positions, that is the data bits at the positions 3, 6, 7, 10, and so on. And the parity bit at the position 2 to the power 2, the parity bit at the position 4, will take care of the data bits at the positions 5, 6, 7, and so on. The parity bit at the position 2 to the power 3, that is 8, will take care of the data bits at the positions 9, 10, and so on. So we can say a parity bit at a particular power of 2 position will take care of the bit positions in which it is a part of the sum as the power of 2. In our example, we have 7 bit positions, and hence 2 to the power 0, 2 to the power 1, and 2 to the power 2 are involved. Thus P1 at the position 2 to the power 0 will take care of the bit position 3, 5, and 7. Similarly, P2 at this position 2 will take care of the bit positions 3, 6, and 7. And P3 at this position 2 to the power 2 will take care of the bit positions 5, 6, and 7. Then how these parity bits will take care of them? By adding the parity bit using either odd parity method or even parity method. Suppose we are using even parity method and this is our data 1001. The positions 1, 2 and 4 will be reserved for the parity bits and the remaining for the data bits. Now P1 will take care of the bit positions 3, 5 and 7. So 3 is 1, 5 is 0 and 7 is 1. So for even parity, if we are using even parity method, then what should be the value of P1? It should be 0. To make the number of ones even. Now the position 3 is having 1, 6, 0 and 7 is 1. So for even parity, what should be the value of P2? It should be 0. And the position 5 is 0, 6 is 0 and 7 is 1. To make even parity, what should be the value of P3? It should be 1. So we have found out the values for the parity P1, P2 and P3. So this is our valid chord word according to Hamming chord. We can see all these are different collections of data bits and each data bit is a member of at least 2 collections. At the receiving side, based on the received data, the parities will be recalculated for check. If any data bit is corrupted, at least 2 parity bits will be wrong. Because every data bit is a member of at least 2 collections. For example, if the data bit at the position 3 is corrupted, then the values of P1 and P2 will go wrong. So at the receiving side, when we recalculate the parities, if we find P1 and P2 is wrong, then we can doubt 3 as well as 7 because the intersection of P1 and P2 is 3 and 7. But since P3 is correct, we can leave 7, hence the corrupted bit will be at position 3. Similarly, if bit 6 is corrupted, then P2 and P3 will be wrong at the receiving side. Thus, if P2 and P3 is calculated to be wrong, we can doubt 6 or 7. But since P1 is correct, then it means bit 7 is not corrupted. Hence we can confirm the corrupted bit is at position 6. And if data bit at position 7 is wrong, then is corrupted, then all the parities P1, P2 and P3 will be wrong at the receiving side. Thus if P1, P2 and P3 are wrong, then the error or the corruption is at bit position 7. And the error may occur on parity bits too. We can see every parity bit takes care of only the data bits, not other parity bits. Thus, if any parity bit goes wrong, it indicates the parity bit itself is corrupted. Thus, in this video, we have discussed what should be the number of redundant bits according to the length of data bits, then what should be the position of the parity bits and which are the data bits to be taken care of by each parity bit, and based on it how we are able to identify the position of error if an error occurs. In the next video, we shall see with an example how to generate the valid chord word and how the position of 1-bit error is detected.